All right, and the last video for this week is going to go through the proof of Green's theorem, or well, kind of, right? So again, just here's a statement of Green's theorem, and then we're going to prove it, but we're only going to do a case. Well, and even within the case, we're doing a case of the case. So, and then you can generalize beyond that. Okay. So kind of our task ahead of us is going to be focusing on a rectangle. Okay, so that's kind of our case. And so we're going to let D be a rectangular region that's oriented counterclockwise, as shown. And so here's our vector field, and so we can go through and verify that this region meets the assumptions, okay, right? Closed boundary region, and then the boundary consists of finitely many simple closed piecewise continuous curves, okay, and then as we traverse the boundary we make sure that the region is on our left, okay. So now what we have to show is that the double integral, or sorry, the vector line integral over the boundary is the same as the double integral. So to do that, though, what we're going to do is show kind of two things. One, we're going to say that the integral of C1 of f dot ds plus the integral of C3 of f dot ds, and you'll notice that these are opposing or opposite sides in the rectangle, that this is equal to the double integral over d of the negative partial of m with respect to y dx dy. Okay, and then similarly we would show, or we will show, that c2 of f dot ds plus integral over c4 of f dot ds is equal to the double integral of d of the partial of n with respect to x dx dy. Okay, and then when you add the two together, on the left hand side you get the entire boundary, and then when you add the right side you get precisely what you want on the right side. So it's just breaking the statement up into pieces. Okay, so we're going to tackle one first and then go on from there. Okay, so first, it would probably be in our best interest to parameterize C1 and C3. Okay, well, if we look at C1 here, we'll call this parameterization x of t, and we'll say that this is, all right, so C1, what we will say is that, all right, we have to let the first thing be variable, but then the second, the y-coordinate is just at c, and we're going to say that t is within a to b. Okay, and then so if we look at the derivative of t, this is just 1 comma 0. Okay, and then similarly when we look at c3, we're going to say that this is another parameterization, say y of t, and this is equal to t comma d, where t is within, okay, I'm going to abuse notation on purpose, and you'll see why. Okay, b to a, technically we would say that this is like b to d, or no, let's just do something else, b to a prime, and you would just define a prime to be the same as a. Okay, it's just meaning that you're starting here and ending there. Okay, and then y prime here is equal to 1 comma 0. Okay, so then for the left hand side, again, that's where I'm adding up those two pieces. Okay, so let's do that. I do integral over c1 of f dot ds, and then plus integral c3 of f dot ds. This is equal to integral c over c1 of f of x of t. Okay, sticking that parameterization in, and then dotted with x prime t dt, and then plus integral over c3 f of y of t, and then y prime, dotted with y prime, of t dt, okay, and then so, and remember that our vector field, just for clarification, x and y, is equal to m comma n, okay, so what this becomes is, so when we do the dot product again, since the y component is 0, we just end up with m from a to b of m of x of t dt, and then plus integral over a to b of m of y of t, close parentheses, dt. Okay, and now we notice that in this parameterization, y, remember that went from b to a, so if we're going from a to b, that's the opposite orientation. So this is really, if we go from a to b, we can do m of x of t just fine, but then we are going to have a minus sign for the opposite direction of, let's see, y of t dt. And let me close brackets here, and dt, okay? So just to then clarify this further, when we do the parameterization here, a to b, or the composition with the parameterization rather, this is going to be m of t comma c minus m of t comma d dt, okay, and that's where I'm going to leave that for right now. Alright, so just kind of leaving that. Now we're going to jump and look at the right hand side. Okay, so the right hand side is again the double integral over d of, and then our claim here, just to revisit it, was that it's minus partial of m with respect to y, minus partial of m with respect to y, dx dy. Okay, and again, so here, if I look at expanding this, this is going to be from a to b, c to d, and this is going to be minus partial of m with respect to y, and then these are going to be the y boundaries. Okay, I'll put that in parentheses just for added clarity, and then so dy dx. Okay, and so then if I go ahead and evaluate this, a to b, and then if I undo this, this is going to be negative m of x and y, and then we have to evaluate this from when y is equal to c to when y is equal to d, and then dx, okay. And so what I get is the integral from a to b of minus m of x comma d minus m of x comma c dx, okay, or put another way, distributing the minus sign in, a to b of m of x comma c minus m of x comma d dx. And so now this has been a lot of calculation, honestly, but what I want you to do is stop and look at what we've generated up here and here. Okay, if you look at them, the only thing that's different between them is the variable. Up here we use t, right? Down here we used x. And when we do the integral, or a definite integral, the variable doesn't matter. It's going to wash out, right? So I think we've accomplished our goal. Okay, so we've done the proof, and for the second part, right, we said we had to kind of put the two together. Number two, you can do the same thing, and there, like, change the parameterization and go through the same steps, and you'll get the same answer. So 2 is going to hold, and that's kind of the proof. Okay. Now what we want to do is be able to extend it, though, because we focus on a particular type of region, and now I want to extend it to maybe cover more ideas. And so I think we can do it, but I want you to pause the video and answer this question for me. How would you prove Green's theorem for each of these irregularly shaped regions using the ideas that we just discussed? Okay, well, if we look at the figure on the left, right, that's almost a rectangle, like we're missing kind of this boundary, right? Or put another way, I think we could actually make this into 2 rectangular regions if we had kind of 2 adjacent edges right here, and I'm separating them by a space, but just know that they're smushed together, where, and then if we had these adjacent edges, then we could do Green's theorem separately for both of these, and we might have one traversing the left part traversing in the up direction as it's shown on the screen, and the right one would traverse down, and then this way we get, over here we get a case where we have the region on our left, so we would have kind of this region, and we could do Green's theorem for that, and then add that result to whatever we get when we do the Green's theorem for the region on the left. Okay, and the idea is that this is okay, because if we look at this boundary here, inserting this boundary, when we do that, and that's a very bad color, when we do that, these end up canceling out, opposite orientation and everything. Okay, for the second one, it's an oval, right? It's circular shaped, and so what we end up doing here in this case is that, well, we can kind of remember our good old friend Riemann and kind of his idea of, okay, taking a region, and so, oh, my pen died, there we go. I want to erase that. Taking a region, and then you're going to divide it into rectangles coarsely, and get, and then you can do Green's theorem for each one of these. You can have fun, and then eventually approximate it, and then take the limit take a limit where you you're adding more and more rectangular regions, so these become smaller, but you're going to get a better approximation. Okay, and then for each of those rectangles, again, just know that we can use Green's theorem and use the ideas that we did in this first region and say everything's going to cancel out, and here's what the region, or here's what the integral is going to be. All right, so I think we can encapsulate most scenarios with the ideas that we showed in this proof formally, and then conceptually we can break a region down into rectangles, and use Green's theorem for most other cases too, where we meet where we meet the assumptions. All right, so that's going to conclude our discussion on Green's theorem, and we'll see you in class soon.